To calculate the electrical service size for the tanning salon, we must first determine the total load in amps. We start by calculating the load for the tanning beds. There is one 60 amp tanning bed, so we have 60 amps times 1 equals 60 amps. Next, we have one 40 amp tanning bed, so 40 amps times 1 equals 40 amps. Then we have three 30 amp tanning beds, so 30 amps times 3 equals 90 amps. Moving on to the heating and air conditioning loads, we have two 20 amp circuits, so 20 amps times 2 equals 40 amps. And one 40 amp circuit, so 40 amps times 1 equals 40 amps. Now let's calculate the other loads. There's a 20 amp, 120 volt furnace circuit, which contributes 20 amps. For the convenience outlets, we have 20 outlets. We'll use 1.5 amps per outlet, which is a standard estimation for general use receptacles in a commercial setting. So, 20 outlets times 1.5 amps equals 30 amps. Now, we'll add up all the loads to find the total load. 60 amps plus 40 amps plus 90 amps plus 40 amps plus 40 amps plus 20 amps plus 30 amps gives us a total of 320 amps at 240 volts. Now, to determine the service size for 120/240 volt 3-wire service, we divide the total load by the square root of 3, which is approximately 1.732. Service size equals total load divided by the square root of 3. Service size equals 320 amps divided by 1.732. Therefore, the service size equals approximately 184.7 amps. Based on this calculation, the recommended service size for the tanning salon is 200 amps. This will provide sufficient capacity for the current load and any potential future expansion. The service equipment should include a meter, a 200 amp main breaker, and a grounding electrode system. Now let's delve a bit deeper into each of these steps, providing more context and considerations. Firstly, let's elaborate on calculating the tanning bed loads. Each tanning bed's amperage requirement is based on its specific electrical characteristics, which can be found on the unit's nameplate. The nameplate will list the voltage, amperage, and power consumption of the tanning bed. It's crucial to use the nameplate amperage rating for accurate load calculations. If the nameplate provides the power consumption in watts, you can calculate the amperage using the formula amps equal watts divided by volts. In this case, all tanning beds were conveniently listed in amperage. Secondly, when addressing the heating and air conditioning loads, these are often significant contributors to the overall electrical demand. In this scenario, the loads were given directly in amperage. However, in other situations, you might need to calculate these loads based on the equipment's power consumption or horsepower. For heating equipment, the nameplate will typically list the wattage. Again, use the formula amps equal watts divided by volts to find the amperage. For air conditioning equipment, the nameplate might list the power consumption in either watts or horsepower. If it's in horsepower, convert it to watts using the conversion factor 746 watts per horsepower, and then use the amps equal watts divided by volts formula. It's important to consider the inrush current of air conditioning equipment, which is the momentary surge of current when the unit starts. This inrush current can be several times higher than the running current and must be factored into the service size calculation. However, for a general estimate, we can use the running current for the initial calculation. Thirdly, the other loads category encompasses various electrical devices and equipment within the tanning salon. The 20 amp furnace circuit is a straightforward load, but the convenience outlets require a bit more consideration. According to electrical codes such as the National Electrical Code, NEC, each general purpose receptacle outlet in a commercial building is typically assigned a load of 180 volt amps, which at 120 volts equals 1.5 amps. This is a conservative estimate that accounts for the potential use of various electrical devices plugged into these outlets. If you have specific information about the types of devices that will be used in these outlets, you can adjust the load calculation accordingly. For example, if you know that only low-power devices like phone chargers will be used, you might be able to reduce the load per outlet. However, it's always best to err on the side of caution and use the 1.5 amp per outlet estimate unless you have very specific information. Fourthly, concerning the service size calculation, the formula service size equals total load divided by the square root of 3 is used to determine the appropriate service size for a 120/240 volt, 3-wire single-phase service. The square root of 3, which is approximately 1.732, accounts for the fact that the load is distributed across 2 phases in a 3-wire system. This formula ensures that the service has sufficient capacity to handle the total load without overloading any of the phases. It is important to note that other factors might influence the final service size selection. Firstly, voltage drop. If the distance between the service entrance and the tanning salon is significant, you need to consider voltage drop. Voltage drop is the reduction in voltage that occurs as electricity flows through a conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. To minimize voltage drop, you might need to increase the size of the service conductors. Secondly, future expansion. It's always a good idea to consider potential future expansion when sizing an electrical service. If the tanning salon plans to add more tanning beds, equipment, or other electrical loads in the future, you should increase the service size accordingly. A good rule of thumb is to add at least 20% to the calculated load to account for future expansion. Thirdly, local codes and regulations. Always consult with local building codes and regulations before installing an electrical service. Local codes might have specific requirements for service size, grounding, and other aspects of the electrical system. It is always best to consult with a qualified electrical contractor to ensure that the electrical service is installed safely and in compliance with all applicable codes. Fifthly, concerning the service equipment, the meter is the device that measures the amount of electricity consumed by the tanning salon. The main breaker is the primary overcurrent protection device for the entire electrical system. It is designed to trip and disconnect the power if the current exceeds the breaker's rating, protecting the equipment and wiring from damage. A 200 amp main breaker is recommended in this case to match the calculated service size. The grounding electrode system is a critical safety component of the electrical system. It provides a low impedance path for fault current to return to the source, which helps to trip the overcurrent protection devices and prevent electrical shock hazards. The grounding electrode system typically consists of a grounding electrode, such as a ground rod or a metal water pipe, connected to the service equipment with a grounding electrode conductor. Sixthly, let's consider some additional information about tanning beds. Tanning beds are high-power electrical devices that require careful consideration when calculating electrical loads. The amperage rating of a tanning bed is typically listed on the unit's nameplate, and it's essential to use this rating for accurate load calculations. Tanning beds often have specific wiring and overcurrent protection requirements, so it's crucial to follow the manufacturer's instructions and local electrical codes when installing them. Additionally, some tanning beds might require dedicated circuits to prevent overloading the electrical system. Seventhly, let's address HVAC, heating, ventilation, and air conditioning systems. HVAC systems are another significant electrical load in commercial buildings. The electrical load of an HVAC system depends on its size, type, and efficiency. As mentioned earlier, it's important to consider the inrush current of air conditioning equipment when calculating the service size. The inrush current can be several times higher than the running current and can cause voltage drop and other problems if not properly accounted for. In addition to the amperage, it's also essential to consider the voltage requirements of the HVAC equipment. Some HVAC systems might require 208 volts or 480 volts, while others can operate on 120/240 volts. Make sure to select the appropriate service voltage and wiring configuration to match the requirements of the HVAC equipment. Eighthly, convenience outlets, also known as general-purpose receptacles, are used to provide power to various electrical devices and equipment. As mentioned earlier, each convenience outlet in a commercial building is typically assigned a load of 180 volt amps or 1.5 amps at 120 volts. This is a conservative estimate that accounts for the potential use of various electrical devices. However, if you have specific information about the types of devices that will be used in these outlets, you can adjust the load calculation accordingly. For example, if you know that only low-power devices like phone chargers will be used, you might be able to reduce the load per outlet. However, it's always best to err on the side of caution and use the 1.5 amp per outlet estimate unless you have very specific information. Ninthly, let's talk about the National Electrical Code, NEC. The NEC is a comprehensive set of standards and guidelines for electrical installations in the United States. It is published by the National Fire Protection Association, NFPA, and is updated every 3 years. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It's essential to follow the NEC when designing and installing an electrical service to ensure safety and compliance. Many local building codes are based on the NEC, so compliance with the NEC will typically satisfy most local code requirements. However, it's always best to check with local authorities to confirm any specific requirements that might apply. 10thly, grounding electrode system explained more thoroughly. The grounding electrode system is a critical safety component of the electrical system. It provides a low impedance path for fault current to return to the source, which helps to trip the overcurrent protection devices and prevent electrical shock hazards. The grounding electrode system typically consists of a grounding electrode, such as a ground rod or a metal water pipe, connected to the service equipment with a grounding electrode conductor. The grounding electrode conductor must be sized according to the NEC, based on the size of the service entrance conductors. The grounding electrode must be properly installed and maintained to ensure its effectiveness. Ground rods must be driven deep enough into the ground to make good contact with the earth. Metal water pipes must be bonded to the grounding system to provide a continuous grounding path. 11thly, concerning service entrance conductors. The service entrance conductors are the wires that connect the utility company's power lines to the tanning salon's electrical service equipment. The service entrance conductors must be sized according to the NEC, based on the calculated load and the ampacity of the conductors. The ampacity of a conductor is its current carrying capacity, which depends on its size, material, and insulation type. The NEC provides tables that list the ampacity of various types of conductors. It's essential to select service entrance conductors with sufficient ampacity to handle the calculated load. The service entrance conductors must also be protected from physical damage and environmental conditions. They must be installed in conduit or other approved raceway and properly supported and secured. 12thly, conduit and raceway systems. Conduit and raceway systems are used to protect and support electrical wiring. Conduit is a rigid or flexible metal or plastic tubing that is used to enclose electrical conductors. Raceway is a general term for any channel or enclosure that is designed to hold electrical conductors. There are many different types of conduit and raceway systems available, each with its own advantages and disadvantages. The type of conduit or raceway used will depend on the specific application and the requirements of the NEC. Some common types of conduit include rigid metal conduit, RMC, intermediate metal conduit, IMC, electrical metallic tubing, and flexible metal conduit, FMC. Some common types of raceway include wireways, cable trays, and service raceways. 13thly, overcurrent protection devices. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect electrical circuits from overloads and short circuits. An overload is a condition where the current in a circuit exceeds the ampacity of the conductors. A short circuit is an unintended connection between two conductors that have different potentials. Overcurrent protection devices are designed to trip and disconnect the power if an overload or short circuit occurs, preventing damage to the equipment and wiring. Circuit breakers are resettable overcurrent protection devices that can be manually or automatically reset after tripping. These are one-time overcurrent protection devices that must be replaced after they blow. The type of overcurrent protection device used will depend on the specific application and the requirements of the NEC. 14th, electrical panels. Electrical panels, also known as load centers or breaker boxes, are used to distribute electricity to various circuits within a building. Electrical panels typically contain a main breaker, which provides overcurrent protection for the entire panel, and branch circuit breakers, which provide overcurrent protection for individual circuits. The electrical panel must be sized according to the NEC, based on the calculated load and the number of circuits required. The electrical panel must also be properly grounded and bonded to ensure safety. 15th, bonding and grounding. Bonding and grounding are essential safety measures that help to prevent electrical shock hazards. Bonding is the process of connecting all metal parts of an electrical system together to create a continuous electrical path. Grounding is the process of connecting the electrical system to the earth. Bonding and grounding help to ensure the fault current will flow back to the source, tripping the overcurrent protection devices and preventing electrical shock hazards. The NEC provides detailed requirements for bonding and grounding electrical systems. 16th, voltage drop calculations are a critical aspect of electrical service design, particularly in installations with long conductor runs or high current demands. Voltage drop refers to the reduction in voltage that occurs along a conductor due to its impedance, which is the opposition to the flow of alternating current. Excessive voltage drop can lead to several problems, including reduced equipment performance, overheating of conductors, and premature failure of electrical components. To calculate voltage drop, you can use the following formula: voltage drop equals 2 times K times I times D divided by circular mils cm, where K is the constant for the conductor material, 12.9 ohms for copper and 21.2 ohms for aluminum, I is the current in amps, D is the one-way distance of the conductor in feet, and cm is the circular mils of the conductor. The circular mils of a conductor can be found in NEC Chapter 9, Table 8. The NEC recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. If the calculated voltage drop exceeds these limits, you need to increase the size of the conductors to reduce the voltage drop. 17th, the importance of a licensed electrical contractor. Designing and installing an electrical service is a complex and potentially dangerous task that should only be performed by a qualified and licensed electrical contractor. A licensed electrical contractor has the knowledge, skills, and experience to design and install an electrical service safely and in compliance with all applicable codes and regulations. They can also perform load calculations, select the appropriate equipment, and ensure that the electrical system is properly grounded and bonded. Hiring a licensed electrical contractor is essential to protect the safety of the occupants of the building and to ensure the long-term reliability of the electrical system. An electrical contractor is also required to obtain the necessary permits and inspections for the electrical work. 18th, demand factors in electrical calculations. Demand factors are used in electrical load calculations to account for the fact that not all electrical loads will be operating at their maximum capacity simultaneously. A demand factor is a ratio of the maximum demand of a system or part of a system to the total connected load of the system or the part of the system under consideration. Demand factors are typically expressed as a percentage or a decimal. For example, a demand factor of 0.8 means that the maximum demand is 80% of the total connected load. The NEC provides demand factors for various types of electrical loads, such as lighting, appliances, and HVAC equipment. These demand factors are based on historical data and are intended to provide a reasonable estimate of the maximum demand. Using demand factors can reduce the calculated load and the required service size. 19th, harmonic distortion is a phenomenon that can occur in electrical systems with nonlinear loads, such as electronic devices, variable frequency drives, and LED lighting. Nonlinear loads draw current in a non-sinusoidal manner, which creates harmonic currents that flow back into the electrical system. Harmonic currents can cause several problems, including overheating of transformers and conductors, reduced power quality, and interference with sensitive electronic equipment. To mitigate harmonic distortion, you can use harmonic filters, which are devices that are designed to block or reduce harmonic currents. Harmonic filters are typically installed at the point of common coupling, which is the point where the nonlinear loads are connected to the electrical system. 20. Surge protection devices, SPDs, are used to protect electrical equipment from voltage surges, also known as transient overvoltages. Voltage surges can be caused by lightning strikes, switching of electrical equipment, and other disturbances on the power grid. Voltage surges can damage or destroy sensitive electronic equipment such as computers, televisions, and appliances. SPD are designed to divert the surge current away from the protected equipment and safely to ground. SPD are typically installed at the service entrance and the branch circuit panels. The NEC requires SPD to be installed in certain applications, such as in dwelling units and in critical facilities.